All right, so we're back. Last lecture, we basically ended with being able to determine what the sign of change in S was for a chemical reaction. So now we want to talk about what if we want to actually put a numerical value to the change in S. How would we go about doing that? So if you remember back when we were calculating the change in enthalpy, we were given a table of figures that showed basically it was the change in H of formation, and that was on page 424. There's a standard enthalpies of formation table there, and so it gave you the value of different substances, their standard enthalpy of formation for those substances, and then we could use those values to calculate the change in enthalpy. Well, we have a similar table for entropy, all right? And so absolute entropies, that table is on page 437 in your book, and similar to the standard enthalpy table that we had, the absolute entropies table is also only good at 25 degrees Celsius. So something to keep in mind. This is at room temperature at 25 degrees Celsius. A couple things I want you to notice about this table. Well, a few things. One is that the unit is joules per mole Kelvin. So that's a little different unit than what we had with change in H, so you need to be aware of that. Also, all the numbers here are positive. This is a measure of entropy, and so it's always going to be a negative value. There's always going to be, it's always going to be a positive value. There's always going to be some entropy, no matter what you're looking at. Also, the table includes elements in their natural state. You'll see that at the very bottom there, where you have carbon and hydrogen, oxygen, as diatomic, homonuclear diatomics. And if you'll remember when we were looking at enthalpy, the value for those would always be 0. But here, there's actually going to be a value other than 0 when you're looking at absolute entropy. So that's important to keep in mind. And then the last thing that I want you to note here is that this table actually proves out what we've said previously, and that is, as you go from solid to liquid to gas, the entropy increases. And so, for example, if you look at water in column number 2 there, you'll see that water in its gas state has a higher value than water in its liquid state does. And so the table does in fact validate what we've previously said, as these measurements have been made for absolute entropies of various substances. And so the way that we use this table, it's an equation that's very similar to the equation that we saw for Hess's law when we were looking at a change in enthalpy. And it says basically that if you have a reaction that you write out like this, little a capital A plus little b capital B, where little a and little b are the number of moles, right, of substance A and substance B, and it produces substance C, capital C with little c moles, and capital D with little d moles, then we could say that the change in entropy for this equation here is going to be this equation here, all right? And basically what that equation boils down to is the same thing that we said when we were looking at the change in enthalpy. It's in essence, the change in S then is going to be the sum of the S of the products, right, minus the sum of the entropy of the reactants. Okay, so that's the equation that we'll use for to get a numerical value for change in S. All right, so let's do a quick example of that, which is on page 438. That example says, determine the value of change in S for the following reaction at 25 degrees Celsius. So since it's at 25 degrees Celsius, we know we can use our table. And so the equation is 2H2O2 aqueous yields 2H2O liquid plus O2 gas. All right, so we're actually going to figure out, we in a previous example, we looked at this exact same problem and determined what the sign of the change in entropy would be. Now we're actually going to be able to get a numeric value for it. So change in S is going to be equal to, we first look at the value of the entropy for the products. So we have 2 moles of H2O in liquid form, And so if you look that number up, it's going to be 2 times 70. Again, our units here are joules per moles K plus 1 mole of oxygen. And so 1 times 205 joules per mole K minus 2 H2O2. So 2 moles of H2O2 in aqueous form. And we see that the value of H2O2 is 143.9 joules per mole K. Right? So we're going to take those values and we're going to plug them in our calculator. And we get a value for change in S of 57.2 joules per K. Because the mole values, remember these were moles. I didn't write my unit on there, but that was 1 mole, that was 2 moles. All right, so moles will cancel out and we're left with those values there. All right, so this is the change in S is positive here in this case. And if you remember when we looked at this in the previous section, we just did a quick spot check and we were able to determine that it was positive because we said that the highest entropy is right here because there's a gas on the product side. And so we take a high number and subtract from a lower number, you're going to get a positive value. So change in S was in fact positive. All right, we'll be back shortly.